vertical asymptotes of rational functions. In this video, we want to identify vertical asymptotes and wholes of rational functions. They both can take place, and we'll see how that works. What do we know coming in? Well, we know what a rational function is from our previous video. Rational functions are quotients of polynomial functions. In other words, it's a function that has a polynomial function in the numerator and a polynomial function in the denominator. And of course, the polynomial function that's in the denominator cannot be equal to 0. Okay, dividing by 0 is undefined. As we learned previously, the domain of a rational function is all real numbers except those x values that make the denominator 0. Okay, so what's an asymptote? Simply put, an asymptote is a line that guides the graph of a function but is not part of the graph of a function. And here's kind of a simple, here's a simple diagram. So here's the function. This function's a curve, the solid line here. And you'll see this dotted line is an asymptote. So the curve is coming down and it's kind of getting guided by this asymptote. And in this case, it's not touching the asymptote. The asymptote is kind of keeping it at bay, if you will. Now this asymptote, you'll notice, is not vertical and it's not horizontal. We're going to learn about both of those. So this asymptote, because it's not vertical or horizontal, this is actually called a slant asymptote. And it's a funny word to say and spell. And we'll be looking at slant asymptotes as well. Okay, but asymptote, a line that guides the graph but is not part of it. They can be, as I just mentioned, vertical, this lesson, horizontal, which I believe is our next lesson, or slant, also called oblique, which is coming up as well. So what's a vertical asymptote? Well, as you might imagine, it's a vertical line. A vertical asymptote, it's vertical. It's a vertical line, x equals a, because all vertical lines are x equals a constant, that guides the graph of a function but is not part of it. So here's the definition of an asymptote. A vertical asymptote is simply a vertical line that guides the graph of a function. It can never be crossed by the graph because it occurs at an x value that is not in the domain. So it can't be part of the function, it's not part of the graph. And a function might have more than one vertical asymptote or whole in that, as we're going to see. So be aware of that. You can have more than one vertical asymptote. And here are some examples. Here's a vertical asymptote, x equals a. And notice as x approaches a from the positive side, which is what this means, as x approaches a with a plus above it, as x approaches a from the right, from the positive side, it's getting closer and closer and closer, and it's going up to infinity. The vertical asymptote is pushing it up to infinity. In this example here, as x approaches a from the negative side, so coming from, and that's got a little negative right here, you can see that the vertical asymptote is pushing the function up to positive infinity. So the vertical asymptote is going to push it to positive infinity or negative infinity. These two examples show you a push to negative infinity. As x approaches the vertical asymptote at x equals a from the positive side, there's the plus, the function is being pushed down to negative infinity. And similarly, as x is approaching a from the negative direction, so from the left, here it comes in from the left, the vertical asymptote at x equals a is pushing the function down to negative infinity. So it's shaping the graph, as we've talked about. Let's take a look at how to find them, and then we'll do some examples. Give me just a moment here. Okay, so how do we find these vertical asymptotes? Well, the first thing we want to do is we want to make sure the rational function is in simplest form as necessary. And then we want to factor both the numerator and the denominator, and then we want to remove any common factors. Okay? And then when we get there, whenever the denominator is equal to 0, we get a vertical asymptote. Okay? It's certainly going to help to see this, because again, I think sometimes just reading mathematical words, unless you're a math teacher, can be a little bit frustrating. It's nice to see some examples. So we want to algebraically, we got 3 pieces here, algebraically find the vertical asymptotes, if it has any. And we're also going to use our calculators to see them, of the graph of each of these rational functions. And then we'll use our graphing device to check our answer. Okay, so f of x equals x over x squared minus 9. Let's make sure it's in simplest form. So I'm going to factor this as x. This is a difference of squares. So this is x minus 3 times x plus 3. Okay. And I'm noticing, do I have any common factors? And the answer is no. I have an x factor in the numerator. I have an x minus 3 factor in the denominator, and I have an x plus 3 factor in the denominator. I don't have any common factors. So I have no, let's make a note here. I have no common factors. Now let's recognize. This shows me clearly that x equals 3 and x equals negative 3 are not in the domain. Okay, once I factored this, I came up with there are 2 numbers that give me a 0 in the denominator. Those 2 numbers are 3 and negative 3. They're not in the domain. Are they vertical asymptotes? Okay, well, I have no common factors. Okay, so both x equals positive 3 and x equals negative 3 are vertical. I got to work on my spelling for asymptotes. A-S-M-Y-P-T-O-T-E-S. Both of those are vertical asymptotes. Let's take a look. Okay, so my graph here, I'm going to open this one up. Y equals, I'll clear what I had out of there. And my function was a fraction. It was a rational, so I'm going to put my fraction bar in. The numerator was an x. The denominator is x squared. Whoops, I could go back to my denominator. Minus 9, that's in the denominator. Now let's graph that. Here comes that. And there goes that piece of the graph of this function, and there's that piece of the graph of this function. And so you can see here that x equals 3, which is the vertical line right here, is shaping the right side of this graph. And the vertical line x equals negative 3 is shaping the left side of this graph. As x approaches negative 3 from the negative side, the function is going to negative infinity. As x approaches negative 3 from the positive direction, the function's value is going up to positive infinity. And similarly over here as well. And we can press our trace key, and we can say, hey, tell me what y value I get when I put in negative 3. And it can't give you a y value back, because there isn't one. It's not part of the domain. There's no y that corresponds to negative 3, no y value. Same thing with 3. We know that 3 is not in the domain. Press enter, and I do not get a y value back because 3 is not in the domain. Okay, let's change that example up a little bit, and I'll leave it so we can see both. I'm keeping the denominator the same as letter A, but I'm changing the numerator to x plus 3. Okay, let's see what that does to this function and our vertical asymptotes. So let's simplify it and get it into simplest terms. The numerator is x plus 3. The denominator can be factored. It is a difference of squares. Oh, take a look. I have a common factor. Okay, so I can simplify. I can take that common factor out. And I'm left with 1 over, x minus 3. Now I want to go back to here real quick, and let's notice x equals 3 and x equals negative 3 are not in the domain. Okay, when I went from here to here, and I factored this, I found 2 numbers are not in the domain. And then when I got to here, I simplified, and I came up with this, okay? And once I get to here, I see I have a vertical asymptote at x equals 3. So x equals 3, because I'm here, and 3 makes this 0. X equals 3 is a vertical asymptote. Now you may be wondering, wait a second, what's negative 3? We're going to get there, okay? But I factored this. I then found, I simplified this. I noticed a common factor. I got it simplified down to here, and this is where I get my vertical asymptotes from. Okay, and this says that 3, the number 3, which is not in the domain, is a vertical asymptote. Okay, we got to deal with a negative 3 because it's also not in the domain, but it is not a vertical asymptote. Let's take a look. Okay, again, we're just looking at right now at vertical asymptote. We're going to touch on holes in just a second. Let's go to y equals, and let's know our denominator changed from x to x plus 3. And then I'm going to graph that. And here comes the graph. And you'll notice that there's where it gets, there's your vertical asymptote at x equals 3. Notice there's not a vertical asymptote at x equals negative 3. As x approaches 3 from the negative side, the function goes to negative infinity. As x approaches 3 from the positive side, the function goes to positive infinity, but there's no vertical asymptote at negative 3. Okay, so what's at negative 3? Well, let's go to trace, and let's put in negative 3, and I'll press enter. As we know, I don't get a y value because I know that negative 3 is not in the domain, but it's not a vertical asymptote. Okay, it turns out that it's a hole, and we'll talk about that in just a few minutes. Okay, so back here, when we've done this, and we've taken out the common factor, we first recognized that we had 2 numbers that are not in the domain. We took out the common factor, and that gave us our vertical asymptote. Okay, that's what we're working on at the moment. We still got to figure out what's going on with this negative 3. And as you know, that's a hole, but let's talk about that in just a few minutes. Okay, letter C. Okay, I've changed up. Let's go back to look at B. Left the numerator the same, but changed the denominator up to x squared plus 9. Okay, well, guess what? There's no such thing as a sum of squares, so this is not factorable, and so there's no common factor, so not factorable. Okay, denominator cannot be equal to 0. Denominator cannot be equal to 0 in the real number system. Okay, we're not going to be playing with the imaginary numbers with this. In the real number system, to remind you, if I take x squared plus 9 equals 0, That gives me x squared equals -9, and there's no such thing. You can't do that in the real number system. So this tells me I have no vertical asymptotes. Okay, nothing. No vertical asymptotes. Let's look at the graph. Okay, let's go back to y equals, and I believe this time I have x plus 3 in the numerator, but my denominator is x squared plus 9, so I'll change that minus to a plus, and I'll graph this, and you can see that line is just going across. It's actually creeping up a little bit over here, and then creeping back down. I can change the window to change the y value, and have the y go from, let's say, -5 to 5. And here it comes. It's pretty close to the x-axis still. Creeping up a little bit, going down and doing something, but there is no vertical asymptote in the graph. Okay, let's talk about holes. We've just discovered how to find vertical asymptotes. Let's talk about holes. Okay. Again, give me just a moment to set myself up. Okay, so in example 1b, the one I was just talking about, okay, where we had the function g of x is equal to x plus 3 divided by x squared minus 9, we noted that there were two numbers that are not in the domain, 3 and -3. As a reminder, we had x plus 3 divided by x squared minus 9. We could factor the x squared minus 9 as x plus 3. Whoops, let's get my parentheses correct. Times x minus 3. Okay, so we had two numbers not in the domain. 3 and -3, not in domain. Okay? And we noticed that when we took out the common factor of the x plus 3, we were left with the one that was the vertical asymptote, which is when x equals 3. So we knew from here, when this was equal to 1 over x minus 3, that x equals 3 is a vertical asymptote. Okay? However, we're still left with the -3, because it is not in the domain, and anything that has a common factor is a hole, okay? X equals -3 is a hole, okay? So a common factor results in a hole at that place. If it's left over, not a common factor in the denominator, that's a vertical asymptote. So here is the graph, if you want to see what that looks like, kind of blown up a little bit. Okay, that graph, remember, that graph had a vertical asymptote at 3. So there's my vertical asymptote at x equals 3. If you recall, the graph did this to the right of x equals 3. And the graph came in and did this to the left of x equals 3. Well, x equals -3, as we plotted it, we would draw a big hole right there in the graph. So that's the difference between a hole and a vertical asymptote. Okay? So again, once you get to here, when you simplify it and remove common factors, that gives you vertical asymptotes. But if you have common factors that you've removed, that gives you the hole. Okay, so I want to keep that in mind. All right, and it's you can't see this on your calculator. Your graphing device doesn't show you this hole. I think I've zoomed in super close, and I can kind of make it happen, but they're just not that sophisticated. Okay, so again, let's recap. As noted above, since the x plus 3 canceled out when we simplified the function, there is not a vertical asymptote at x equals -3. What there is instead is an open circle on the graph at x equals 3. This is next to impossible to see. However, when we checked the value at x, the y value at x equals -3, we saw that there wasn't one. Okay, so zeros in the denominator are either vertical asymptotes or they're holes. They're one or the other because they're not in the domain. A rational function can have any number of vertical asymptotes and any number of holes. I don't think we'll get too complicated, but you can have any number of vertical asymptotes and any number of holes. Let's do another example. We can see this come to play. We can see this come into play. Algebraically, find the domain of the rational function below. Determine if those numbers in the domain are vertical asymptotes or holes. If they're vertical asymptotes, write the equation of the line. So we're here. We have a quadratic in the numerator and denominator. Let's simplify it. So this is 5 times, I'm going to factor out the 5, x squared plus 5x plus 6. And I can factor the denominator. The denominator is factorable. It is x plus 2 times x plus 1. Okay, so now let's go over to here. Let's factor this quadratic. 5 times. This one is x plus 3 times x plus 2. And that's over x plus 3 over x plus 1. Okay, so now what do we know? We know that -1 and -3 are not in domain. Okay, they both result in a 0 in the denominator. Okay, which one? Are they both vertical asymptotes? Are they both holes? Are they 1 and 1? Well, if we simplify it, we have 5 over x plus 2 divided by x plus 1 because x plus 3 is a common factor. This tells us we have a vertical asymptote at x equals -1. If vertical asymptotes, write the equation of the line. There we go. Okay. However, did I make a mistake in something? I did make a mistake. Oh my goodness. I made a mistake. This is x plus 2. I'm looking at my notes. Okay, so you need to rewind the last about 1 minute. And let's get myself straightened out here. Okay, I goofed. My apologies. It happens. We have erasers. Thank goodness. Okay, let's go back to here. Okay. I goofed up when I did my factoring, when I copied my factor over. Let's repeat this a little bit so we're all on the same page. I factored this quadratic and I got x plus 3 times x plus 2. This quadratic factored to x plus 2 plus x plus 1. And this is, so it's the same, x plus 2 plus x plus 1. And so -1 is a 0 and, whoops, this is a -2. Sorry about that. So the two zeros, the two numbers that are not in the domain are x equals -1 and x equals -2. When I simplify, the x plus 2's are a common factor and I get this simplified. And the simplified version tells me about if I have any vertical asymptotes. And I do. I have one at -1. But I can't forget the -2 here. Okay. So therefore, 3 dots means therefore, I have a hole at x equals -2. Sorry about that. Perfection is elusive. I'm not perfect. Okay, so what does my graph look like? Let's just take a look at it. We won't sketch this. Okay, so y equals, I'll clear that out. I'll put in a fraction bar. And I've got 5x squared plus 25x plus 30 in my numerator. And I have x squared plus 3x plus 2 in my denominator. If I graph, let's go to zoom standard. So number 6, here comes the graph. So there's the graph, and looks like we're way up high here. So let's see if let's move my, let's get my y-axis extended in the upward direction. So let's let my y go, y maximum go to 25. Let's go to 30. And we'll count that one by tens. Okay, so there's the left part. And here comes that's better. Okay, so we can see at x equals -1, there's that vertical asymptote right there that's shaping the graph vertically. Okay? But we know that -2 is also not in the domain. But it looks like -2 has a point right here. If we go to trace and we put in -2, you'll notice there is no y value. So that is the hole at -2. So, find the domain. Okay, so the domain. I think I'm still on the page. Yep, the domain. In interval notation, from -infinity to -2, that's a hole. And then from -2 to -1, -1's a vertical asymptote. And then from -1 to positive infinity. That's interval notation. In set builder notation, we can say all x's such that x is not equal to -2 and comma, x is not equal to, not equal to -1. Okay, so when you get to this stage here, as you've simplified and factored, if it's a common factor, it's a hole. If it's not a common factor in the denominator, it's a vertical asymptote.